So, first of all, let me thank Stefano, who gave me the opportunity and the possibility to speak about what I recently did, and Michael gave me the opportunity to make this 4 hours small course in what he explained, what he explained. Okay, so in particular, Stefano asked me to make to speak about what I recently did in thermodynamic formulas for random dynamical system, in particular, quenched random dynamical system. And at the same time, to give to say some words about what I did on extreme value theory. I mean, I became involved in extreme value theory a few years ago. First of all, I worked since 20 years, more than 20 years, on recurrence property in dynamical systems. Then people working in extreme value theory came to me, and we began to work together because there is a close connection between recurrence and extreme value theory. You will see in some cases they are basically the same thing. But then it turns out that what we did on a mathematical level for extreme value theory could be applied to some climate stuff. In particular, I did several works with people who are now in Paris, in particular Davide Faranda, who is an Italian guy who studied in Bologna, then he immigrated in France, where he has a position at CNRS, and his collaborators, in particular Pascal Yu, and also at the beginning with Valerio Lucarini, that everyone knows, and with him and other 7 collaborators, we wrote a book published by Wiley, I think, yes, which is called Extreme Value Theory and Dynamical Systems. The good reference will be soon on the screen. And in this book, we collected what we did in the last years on the application of extreme value theory to dynamical systems. And there are, okay, the book is available for free. For instance, if you go on my webpage, you can download the book. And this book has been written, as I told you, we are 7 and 8, I don't remember now, probably it's written later on. And on this book, at the same time, we reported rigorous results which we established in the context of dynamical system, plus application to climate, in general to nonlinear physics, and in particular to climate. Okay, what we did was more or less around maps, not flows. For instance, what Michael presented this morning with this perturbation of Lorentz attractor is we cannot do it for the moment on a rigorous, using our technique on a rigorous basis, but of course this is the goal, because the nature is more, especially described by flows on by man. But okay, we are working, by the way, with Stefano and Paolo and Franco Flamboli on extreme value theory applied to random, to a stochastic dynamical system, and the approach which we used was the Annealing approach. I will try to explain, at least in the context of maps, even perturbed, what is the difference between quenched and Annealing. Annealing, we are doing together. And just this morning, looking at the beautiful picture of the Lorentz attractor, it came to mind to try to develop what we did in the quenched setting, because it would be nice exact, beautiful flows. But we are far from it. By the way, if someone is interested in extreme value theory, there is a fundamental book, I will give the reference to this book later on, by 3 specialists, Leadbetter, and others to do for what we mean, Lindgren and someone else. And They also look at extreme value theory for flows, but it's not easy. It's very difficult to understand what they did. I don't know if you know about the result of extreme value theory for flows. In this book, there are something, but the assumption, the hypotheses are really some cases very difficult to check. So we are not there. We are just looking for that. But at the same time, Stefan asked me to speak about a random dynamical system. So what I try to do is to mix together random dynamical system applied to extreme value theory and the other way around. So when we speak about extreme value theory, I will have in mind the application for random match. I will try to do both. In the second part, which we probably begin today and will continue next week, I will give more details about recent papers we put on a card just 1 month ago, where we did the extreme value theory for quench dynamical system for a large class of potentials. Okay, you will see the notation is heavy. I mean, we have not to be discouraged because I don't know how to present it in a different way. I mean, there are a lot of assumptions, unfortunately, and the notation is not easy, but it's just a notation. And I don't know if there is other way to present this quench dynamical system, even in one dimension, by the way, in an elementary way. I don't know. I mean, let's see what we understand. It's not important to understand everything. What is important is just to have an idea of the result and what kind of system we apply it. Then you can go to the references and look to the technical part. Okay, so let's start to be more concrete. Okay, so this is exactly what they tell you now. There are sentences, and you insist on dynamical systems which are perturbed by some kind of noise. Now, let me tell you the kind of noise which I consider. As Michael told you this morning, the fundamental book is this book by Ludwig Arnold, Random Dynamics, which is really good book. There are also Kiefer books. Kiefer, I forgot. I hope Kiefer is not looking to me because otherwise he'll be just upset. But he wrote 2 books on a random dynamical system, but Yuri Kiefer. But these 2 books are, I think, especially devoted to a need dynamical system, which is what I mean. Instead, his paper, he wrote a lot of paper, are on both aspects, a need and quench. Okay. So, the starting point is exactly what Michael told you this morning, but the phase space, okay, the phase space is whatever it is, but instead of philosophy, we consider maps. But there are a lot of similarities between what Michael told you this morning and what I'm going to tell you now. So we have a phase space which, okay, this phase space, you will see, I will take it during this lecture as the open interval, 0, 1. You can ask if this is not a too strong reduction. The question is, yes, it is. But the point is, we can do the theory which we developed for the moment only on the interval. It's still open to do it on higher dimension. For instance, last week, what I'm telling you now is just to motivate someone to do something in this field. Last week I spoke with Scarangelo, who is one of the experts in dynamical systems, and I told him that what I did for quenching dynamical system for general potential in dimension 1 is not immediately generalized to other dimension, and he agreed with me. There are no, it's complicated. I will tell you why it's complicated. And I have a student of mine who is fighting to try to apply what we did in higher dimension, and there are problems. And you will see if you study mathematics, I will tell you the problem, where the problem is. Because sometimes this kind of problem, one under-evaluated this problem because he could say, oh, it's just an academic problem. No, it's not. I will tell you, it's just a measurability problem. Usually people don't care about measurability. It should came for free. It doesn't in this case. And this is crucial for us. Okay, I will tell you where the measurability came later on. Okay, so for the moment, okay, but by the way, next week I will give you, I will present you still a quencher theory, which we develop in a slightly different context, and in this case we can apply it to higher dimension. But for extreme value theory, we are not taking that. So what we confined our theory to one dimension, and I will tell you where are the technical problem later on. Okay, so basically we have a probability space omega Fn, and on this probability space we associate to each omega a map. Okay, for the moment, please. There are, if you do mathematics, I know you not happy because I did it for the moment. Write explicitly all the assumption. I did it with some intention because this first part is colloquial. I mean, I will try to present you the result in an easy way. But in the second part, which could start today or next week, everything will be defined very good. So for the moment, we should have some way to associate to each point in this omega. Usually, you know, where is the point? No. Okay, so on this space, probability space, we have a map acting sigma, right? It's exactly the framework that Michael told us this morning. And for me, I will take sigma for the moment invertible and ongoing. So you will see the invertibility of sigma will play a role in the difference between a nil and quencher. I mean, since I will mostly be interested in quencher, I will take sigma invertible. But I will give you also an example where sigma is not invertible, and this is useful if we want to approach the randomness from the nil point of view. Okay. Okay, now for each omega, I take some map, I associate some map. I will give you an example in a moment how this association can be done practically. And then I compose this map. Look, the composition is, okay. So the association moves in this way. I take omega, sigma n minus 1 omega. Okay, so this shifting from one of these index to the another one is done using a deterministic map. Right? This is typical of the quencher frame. Instead, in the nil, you will see this association will be given by IID value. This is one of the examples. You take a sigma and the rational rotation of the circle, and this bar means the modulus 1 operation when you take half irrational. And then we do the following. We take our space, which is completely arbitrary for the moment, right? And then so it's a subset for this of R. We take a partition in omega J set, a finite partition, and then we take the map design in this following way. When omega belongs to sigma J, on this sigma J, the map is constant. I give a picture in the next slide. And then, for instance, T3 omega is written in this way. I take a point T, I apply the map with this sigma, omega, then omega plus alpha, model 1, and so on and so forth. So it's very easy. And okay, so you see the situation. I have my space omega, I put a finite partition, and on each omega, I define for each omega into this set, I have only one family of map, T omega. Then I move to another element of the partition, and the map is T sigma omega, and for all the sigma omega, I mean, for all points of this sigma omega, the map is the same. Works in this way. This is one way to move sigma and to associate to sigma a map. There are other ways, there will be other examples later on. And this is the second example. The second example works in this way. we take omega, which is we have a finite alphabet of L symbols, and to take the infinite product on the left and the right, in the past and the future, and they take sigma, the bilateral shift. And sorry, in the previous slide, I put the measure on the probability space. I call it n. I forgot to change it in theta because n later on will be something else. So I'm sorry. I thought I would change it all there in theta. Theta now is the measure of the probability space, which I put n before. I will correct later on in the slides. And I take theta, any ergodic measure, for instance, the Bernoulli measure on the subshift. And then take a word with just an infinite sequence of symbols, each one belonging to this alphabet, and to each omega, which is an infinite sequence, I associate directly in this way. First of all, to each of these L symbols, I associate a map. Right? So I have L symbols. To each symbol, I associate a map. I will tell you later on how we choose this map. For the moment, I will tell you how this association is done. And then, when I take the word omega, I take the map associated to omega, which is the map which is associated to the omega 0 symbols. Omega 0 is a symbol in omega, and each of these symbols belong to this alphabet. So basically, when the omega is just the map associated to the symbols, which is just sitting omega 0, which is the starting point of omega. Why this? Because, you know, when you iterate, you see what's going on. First of all, sorry. Yes, no. You see what is going on. This is the first. Then we go to the second. But the second one doesn't mean. It means that I have to iterate sigma. If you iterate, I have to iterate omega. But if you iterate omega with the shift, instead of omega 0, you will have omega 1. So basically, here I have T omega 1, because omega 1 becomes the 0 position at sigma omega, and so on and so forth. So in this case, you see, it's very easy to describe the concatenation of this map. You just fix an infinite word, and the map follow each other, just following the symbol in the infinite word. This is one very common way to generate this kind of random errors. Pay attention, because this example I will describe immediately one of the slides. If this example is considered not in this setting, but in the annealed setting, we will have a different way to interpret this object. Okay, but let's continue for the moment with this kind of approach. Right? Then we consider function defined for each point x, which is in the phase space, right? But also this observable could depend on omega. At this moment, I will show you a bundle of spaces moving with the nodes. I will do the same later on. In this framework, if you want, instead of considering only one phase space I, we index this phase space by omega, and we call this fibers. But for the kind of example which I will give you, we can consider all these fibers which are equal to the phase space I. And in the same way, we consider a concatenation of maps. Even the observable will be considered on different fibers. Of course, I forgot to put here the evolution of the point x. I forgot to put it, right? Because if I have x here, here I should have, if I move x here, I should have the evolution of the point x as well. Okay. Now, let's move a little bit more forward. Okay, the above construction allow us to define a deterministic dynamical system, which is called the skew system. Okay. So basically, you define a map with two variables, let's put it this way, omega and x. Each belong to our phase space I. For the moment, it's not really, it's not necessarily a subset of R, right? It could be anything for the moment. And omega is in our space big omega. And this define a deterministic dynamical system, which is called a skew system. So for instance, what is T2, T squared? Iterated twice. And then if you take T iterated twice, you will have, so what is it, for instance, T squared omega x will be sigma squared omega, and here we have T omega, T sigma omega x. It works in this way, right? And, okay, but in the mid case, in the coincident case, which is what we are considering now, we don't consider this part of the dimension. We only consider this one. So you see, it works in this way. We take, okay, let me see. Okay, suppose, okay, let me put this in this way. I have here omega, and here I have I, right? So you take a point here, which is omega y, omega x, sorry, omega x, and then you iterate it. If you iterate with the map T, look, T, there is this T is different from this one, okay? Okay, I should call it S, as usual in the book. Okay, I will correct it as well. But I call it T, this one. So what happens here? If you have this point here, you move here, and you have the point sigma omega, T omega x, right? And then you move to this point here, and you have this point here, which is sigma omega, square omega, T sigma omega, T omega x. Okay? Now, the evolution from this point to this point is completely deterministic because it's given by this map. But we don't look at this. What we look is to the projection here. And this point here, right, we call this point random in some sense. In some sense, we call the distribution of this point random. Now we will precise how to measure the randomness, what measure put here, it will come in a moment. But the randomness is exactly in this way, you see? We have a purely deterministic dynamical system in the skew product space, I time omega. The evolution is completely deterministic. Then we project on I, and we follow and we try to describe statistically the distribution of this point. And we call the distribution quench. Because of course they depend on omega. If you change omega, everything will be different. So the question is, we have to put a measure here which takes into account omega, you see? So if you want to do, you know probability, so you know better than me, we need some probability P to describe the distribution of this point. But this probability must take into account two objects. Let me call mu one of this probability. Of course, this is a measure. Of course, this measure here should take into account, so let me call, if you prefer, d mu x. This measure should take into account the point x, which is on I, some point here. But also, we have to index this measure with the choice of the randomness omega. And we put omega. If you remember, in the talk by Michael, there were these guys, which I call equivariant. Michael called sample, the same, exactly the same. I know, like I prefers samples. Why I use equivariant? Because equivariant is used for people doing multiplicative algorithmic theory, where this object play a fundamental role. But it's a disintegration formula, we didn't. But Michael really anticipated this, because this integration formula is exactly the same. Okay? Okay, so let's continue. Okay, here it is. Now, I promised you that I will try to make a difference between a need differential. Okay, I don't pretend this is exactly the only way to distinguish between the two. But I try to follow what is written in Arnold Wood. I repeat, I'm not saying this is the best or the only one difference between the two frames, principle and need. But this is what I learned looking at Arnold. Right? Okay. Okay, first of all, let's be more formal. We have this dynamical system. This is deterministic. So the first question when you have a deterministic dynamical system is, can I construct invariant measure? And if yes, or not, mixing, whatever. So, and in dynamical system, usually we want to have a probability measure, right? So then let's denote pt to omega time I, all the probability measure mu on this product space with marginal theta. What does it mean? It means the following. It means that if, it is written by the way, but if I take some function f, this is a double integral with two variables, okay? What does it mean, a marginal theta? It means that I should be able to write it in this way, f, some intermediate measure, which will become our sample measure, then in x, then something, this measure here is done from the very beginning, is the margin, theta, right? So the idea is, I have this measure mu, I want construct all this measure if they exist, for which I have this integration here. Right? So this is given, but is it possible to write it in this way, from here to here? Now, if you look at one of the papers which Michael quoted this morning, if you like measure theory, you'll be happy. This is a paper by Owen. He belongs to the Arnold School. And he gave, a probably written later on.
You're missing an A.
Craft, sorry.
Don't accuse him of being
Okay. There is written the assumption, you know, that I think is written somewhere, or probably I wrote in the paper, but there are very general assumptions. A Polish space, you know, this kind of stuff, like abstract. I mean, in another situation, if we have an invariant measure, if we have mu, this is the key point. If we have mu and a marginal, we can get this stuff here. But first of all, we have to get mu. And it's not so easy to get mu. Okay. Okay, so well, this is okay. Yes. Okay, so the idea is suppose we can do it. So I want to be precise. Suppose we can construct an invariant measure for this system. Okay, first assumption. Then we have our theorem which allow us to get this family of measures. Okay. Then it is easy, not easy, it's an exercise in measure theory to prove the following. The push forward of mu omega in mu sigma omega. So basically, well, the push forward, you know what it means, right? Okay. This guy here. With this one, right? And this measure here is exactly equal to mu sigma omega. A is any measurable size. Okay. So this is a fundamental relation. Why? The idea is, I told you that we have to follow and to describe the statistical distribution of this point on this vector space, right? If this point were distributed according to an invariant measure, so if the dynamics is deterministic, any invariant measure is satisfies this with the same index, which is the definition of invariance in the dynamical system. But here, these points are not distributed according to an invariant measure because this point came from this construction. And in fact, the distribution we have to look for is with this kind of measure, which has this property. It's called the equivalent property. But this is important, very important for the following. This is true if and only if sigma at the beginning, the driving system is invertible. But this makes the difference, I mean, what understood, the difference with the need situation which came later on. Okay. So, for us, the type T omega, V omega define what they call a quantidynamic system. And the statistics on this space, factor space, namely statistic mean, if you want to do some probability, central limit and whatever, they have correlation, we have to use this measure mu omega equivalent to central measure. Or sometimes in the books of mathematics we call it a conditional measure. Right? So this is the situation. Now the second question. Now some people could ask the very natural question. Okay, you see, here is a disintegration formula, right? But is it possible that is it possible that this measure is a product measure, right? So here it is not. So if you want, in a very colloquial way, this measure depends on the value of the sphere. It's not a product measure on the two species. So it's possible to have product measures. And if yes, what does it mean? Okay, so then now this brings us to the need case. Okay, this is the need case.
My problem between the body and omega are the same.
I mean the following. Is it possible that the measure on the skew system exists independently of all my previous considerations, right? Is it possible to write it, for instance, in this way? If yes, this we have all the same image, omega. Is it the same?
So, omega, mu omega will be equal to 3.
Yes, the omega, this one will be wrong, exactly. This is exactly, this brings us to the annihilation.
In this sense.
Yes, exactly. But this, the invertibility of sigma plays a fundamental role. Okay, so let's do smoothly here. Okay, first of all, I tell you again what I said before. Mu is the invalid measure for the skew, which is a deterministic system. It could be written in this way, okay? If it exists. Then by Crowell's theorem or Lagarde's theorem, even there is also Rockley. Probably Rockley was the first one. Is big paper on measure theory, disintegration measure theory. I think everything is Rockley already, right? You can write it in this way. Now, when sigma is invertible, what I told you before, when sigma is invertible, right? Mu omega is equal to rho, so this measure becomes a product measure if and only if, all, you see, basically I have this, all the mu omega are the same. So basically, you see, I can put here T omega, and I have, for almost all omega, I have this invariant property. So it's a very strong one. In fact, if you read Arnold's book, he said, this happens rarely, and he's completely right. If I give you an example, any example of coincident orbital system, and you take sigma invertible, then it's very difficult that all the mu omega will be the same, all these guys will be the same. It could happen, but I mean, it's very rare. It's not very interesting, but it could happen. Now let's go to a different scenario. Suppose now we suppose that sigma is not invertible. Right? For instance, in the example which I told you before, when you have the shift, you take only the alphabet to the power n. So basically, you take this space here, omega plus, which is 0, n minus 1 to the power n, and you take the shift on this space into itself. Right? This is just only the shift only in the future, and this is clearly not invertible. And what happens in this case? Now, suppose sigma is not invertible. Then the measure mu, which is, I repeat, again, the invariant measure of this Q, can be written as a product measure if and only if rho verifies some particular property, which is this one. This is important because people working in a need case, even Markov chain, they use this one. So what does it mean? It means I take my observable, which depends for the moment only on the point x, and I compute this observable in T omega x. I integrate at the same time with respect to the point x and with respect to the noise, and it gives me exactly the average of f on rho x. This is called the stationary measure of the system. Okay, so this is the huge difference between quencher and anneal. In the quencher case, the statistics will be given by a rho, which is exactly the mu omega when the mu omega are the same, if you want. And this rho doesn't verify the equivariant property. It doesn't verify this equivariant property. I mean, it verifies a stronger property, namely, we have it for all omega, because mu and mu sigma omega are the same. Right? And we have this property here. Now, let me give you an example how we can get this scenario here. Probably Stefan already told you last week how to generate this anneal situation. I'll give you one example. Okay, so let's do the following. Take one space omega theta. Omega theta is any space for the moment. It is not necessarily sequence of numbers on alphabet, whatever you want. And then we take it to the power n. So we take the product only in the future. And then we take a measure on this big space, which is the product measure of some measure theta, which lives on omega theta. So basically, I take one space, which is omega theta, is something larger or whatever, let's call it F, and here I put this theta omega, right? This is a probability space, and then I take the derivative product on the future. And then I take the shift on this space. Okay? So I have the space, the measure. I take this is the basic space. Then I take the derivative product, and on this derivative product, I define the one-sided shift. And in particular, it's not finished yet, to each omega in this basic space, I associate a map, T omega. So I have this space, the first, the first element of the sequence of space which I'm going to construct, our basic space. It contains some letters. Then we call this letter omega alpha. To each omega alpha, I associate a map T omega alpha in some way. For example, this one, I don't know, could be the previous space 0 and minus 1. And this omega alpha is one of the letters in this address. But it could be an integer. It could be an integer. And then what I do is the following. Yes, then, okay, so to each omega in this basic space, I associate a map, for instance, this association here. And then I have to define a map on this big space. So what I do something which is very close to what I did before. So I take this infinite sequence of letters, because this guy belongs to this product space, and associate to it only the first symbol. Here I started from omega 1. I could start from omega 0. In this case, we associate omega 0. But I brought omega 1. Okay, so I take the first one. And so you see, the concatenation gives us exactly what we had before. But now, the measure here, you see, this measure is a product measure. So this association, omega 1, sigma, omega 2, when I follow the shift, give us I am the sequence of variables. Okay? So basically, the message is the following. If we take, this is another way to speak about a need, the choice of the matrix IID. Okay? I did it differently. I took this point of view, I take the point of view to say that I have a stationary measure if and only if the measure on the skew is a direct product. This is equivalent to say that the choice of the maps, one after the other, is given by an IID process, because this is an IID process. The probability here, this probability here, is a product probability, and we still knows if this is a product, the variable are independent. Okay? So this is another way to look at this and case. Okay, this is another way to write the stationary measurement, looking to sets instead of integrating bounding function, but this is exactly the same. Okay? Now, pay attention, because look what happened here. What you see, the idea is that this measure rho, wait a second. Yes, there is a mistake here. This is, yes, theta to the power n, sorry. Okay, so, no, this is an important point. Yes, sorry.
A small general question.
Yes.
From the interpretation you are giving now,
yes,
it seems to me that the sequential approach becomes more important when the noise is not IID.
Exactly.
In some sense.
It's exactly this one.
This is the right direction where to go. Why when you have IID, the two points of view are strongly connected.
Yes, but also the invertibility of the driving system is important, because, for instance, if you can do this, even in the if you take how to say, this construction here can be done even if I take, instead of n, I take z.
Yes,
but
is that once you take a shift, you can take it bilateral or
yes,
bilateral. At the end, you can.
Yes, but if I take z, I cannot define. I mean, this equivalent measure doesn't exist anymore unless all the mu omega are the same. This is what is written in this result, which is an if and or if. So if I can do the same exactly, taking this to the power z. But in this case, I do not have anymore this equivariant property unless all the mu omega are the same. So if I lose the dependence on omega, it becomes like it. So I take, basically, I recover a stationary measure. It gives me the statistic, the probability to study the distribution of the points.
When the base is ergodic, in some sense, don't you go towards almost everywhere constant thing, always, or?
Yes, but here I don't think the ergodicity play a role in these definitions for the moment. Because what is important here is the invertibility or not of the map C. The ergodicity came later on to define, but I'm not completely sure what I'm saying. I don't remember now, or this proof is not very difficult, but I don't see the ergodicity. Only we use invariance and some measured theoretical stuff. But I can check. You can check. By the way, there is a mistake, not a mistake. I forgot to put here rho to the power theta to the power n, right? I mean, not really, because this was just a reminder of what I did before. Okay, no, it's correct. Now, what happens? The measure on the school system in this framework has this structure. Look, is rho, which is the structure of time, the measure on the basic space to the power n. But the stationarity formula is only in terms of the measure theta, here. But this is an important point. Okay, I repeat. This part here is correct because I refer to what I thought before. So I said, okay, suppose you have a measure mu, which can be factorized in this way, right? Where theta is the marginal, and rho, if it exists, defines a stationary measure which verifies the circle. Good. Then I told you, let's try to construct an example. The example works in this way. I have a basic space with measure theta. I take the product of this measure, and the product means I'm looking to IID variable. And then what I got is the measure mu of this Q can be written in this way. The product of the stationary time the end product of the measure on this basic space. But what is interesting is the stationarity, which now is written here in another way, is given in terms of the measure theta on this place. So we don't need this product measure in order to establish stationarity. The stationarity is established only with respect to theta. It is exactly what we do. For instance, if you have a system which you want to study in the mean situation, if you want to prove a stationary measure exists, you have to verify this formula here. This is exactly the formula which gives you the stationary measure for macro chain. In order to prove that a macro chain has a stationary measure when the macro chain is continuous, if it exists, it is the eigenvalue of some operators. Not written in this way, of course, because in the macro chain we don't have this guy, but we have the evolution operator, we have the macro operator. But what intervenes here is just the measure which is on this basic space. But the measure on the skew is given by this one. Now, why I'm telling you this? Because if you take the need situation and you take, if you take the need, suppose we take the need situation now, and I take xn, a random variable that depend on omega and on x. For instance, suppose this is just some observable f computed on some random orbit. This random orbit is writing here means t omega, t sigma n minus 1 omega applied to x, right? So this is a random variable. And this measure here, this one, this measure here, where is this one? The measure mu, which is sigma theta to the power n times the stationary measure. This measure here is stationary for this random process. So stationary in the probability sense. If you take n random variable and you shift the distribution of the first time variable is independent of shifting this measure. So, for instance, some statistical theorem, for instance, the central limit theorem, in the need situation, are proved using this measure. And in some sense, they are not too difficult. The difficulty is when we are in the quencher case, because in the quencher case, the process is not anymore stationary in the probabilistic sense. Because we don't have. Okay, this is an easy exercise to prove that if you take, for instance, this sequence of variables, defined in this way, with this measure here, this process is stationary, which is better this product measure. But in the quencher case, it's not. And so, for instance, if you want to prove the central limit theorem, you don't tell anymore the central limit theorem for stationary process. You have to go to random central limit for non-stationary process. And in this case, it's better to use martingale techniques because there are formulations of the CLT in the non-stationary process using martingale. This is exactly what we did. And I will tell you next week how we did the central limit theorem and other limit theorem for the quencher situation. But for the need, it's not completely clear, but we did it. We published a paper a few years ago with Mark Nicol and Romania, on transaction of American Mathematical Society, where we gave all the limit theorems which we give at the moment for this kind of system, a need system. Yes. But they were established with respect to this product. In some sense, it's not too difficult, but still something to do. Okay. Yes. Okay. So something interesting is if you have the need situation, to the need situation, it is possible to associate a Markov chain, a continuous Markov chain. So basically, when you are in the Markov chain theory, you have to give the following quantity. You have to give the initial distribution of the chain, and then you have to give the transition probability, which usually are written in this way, which is the probability that xn is in A when xn minus 1 was equal to x, right? This is the transition probability. Now, if you have the need situation, you can always construct a Markov chain which is associated to it, where the transition probability, I call it U instead of P, is given by this formula here. So theta is exactly theta now. So the measure on this basic space, not the power n, this is theta, of 4 the omega for which T omega belongs to it. So this is a very powerful way to construct Markov chain. So basically, if you have the need and the need in the system, you can associate it to it a Markov chain. And the other way around, but with some assumptions. If you are interested, the construction from a Markov chain from a need system is done in Kiefer book, in the first Kiefer book. We recently used in our paper, I can tell you if you want, but the straightforward way, namely to go to the need to the Markov chain, is always true. You define the transition probability, namely this guy here, in this way. and you have a continuous market change. Okay. We continue. I mean, you want to stop or we continue? Okay. We can continue. Eventually we stop.
I think when we are like at half of what you want to say in the output, we can make a break.
But if you want to make a break, I did, otherwise I continue. Eventually we stop.
We can go.
Okay, I didn't stop a little bit earlier. Okay, now let's go to the strain value theory, because this was also something. Okay, I will speak about this theory. First of all, for random numerical system, because this was the goal, to mix randomness and extreme value theory. And then I will tell you how we can get some result in the quantitative setting. But this is just a new word. I know you were at the end. Instead, in the new situation, for example, we did a few years ago. Okay, so there are two fundamental books. One fundamental book, which is the book I quoted before, Extremes and Narrative Problem. This is very nice. The other book is not fundamental, so it's our book. I quoted it because it's just for the numerical system, but okay, you have to read the first one. Okay, I told you how many we are. 1, 2, 3, 4, 5, 6, 7, 8, 9 in this book. Okay, and each one gives us one of a chapter. Anyway, so now I try to start in a very general way, and I repeat something, of course. Okay, so at the beginning we have an analytical system, right? And which is now, for the moment, given by a species, image, or whatever, measure mu and a metric. Then, okay, in the extreme, okay, so I will, if you know extreme value theory, you will be not happy with what I'm going to tell you for a reason. Because I will basically look, okay, in the extreme value theory, it's like the central limit theory. In the central limit theory, we go, at the end, we get the Gaussian distribution, right? Here we get, at the end, 3 distributions. Weibull, Fenchel, and Gumbel. Here we speak only about one. Why? Because it's, in some sense, is related to the dynamical system. Even the others, but this one. So this doesn't cover all the theory. So in particular, I will get this limit law. You will see how, starting from one particular observable, which is this one. So then this observable is minus below the distance from a point x from a given point z. Right? You will see in a moment the meaning of this observable. So basically, this function becomes infinite when the point x approaches the point z. Now, you have to keep in mind the following. Z is a point given. And if you want, a neighborhood of Z is a rare set. You will see why in the next slides. So Z is the point where I want to see what's going on. For me, it's the rare set, the exceptional set. And this observer allows me to approach this point. And when I approach this point, this function goes to infinity. Now I'll give you a geometric interpretation of it in a moment. Then I take a random transformation. Now I get in the index set, right? Because I want to give you the term first in the index set. I take a random transformation given in this way. You see? So I repeat what I did before, but in a much easier way. I take a map G, which is the map given from the very beginning, and I put omega mod 1. Okay, so it's a map of the circle. And this omega is chosen in some interval, minus epsilon epsilon, and all the omega are chosen in an IID way with distribution theta, epsilon. Now, an important observation. Why I put now epsilon here, I didn't put in the previous transparency? Because if one in the mixed situation, and now we are in the mixed situation, there is an important issue which we don't tell in the quotient situation. Namely, we could have, of course, Then I will ask Michael about it in the question. But for the moment, let's concentrate on this unique situation. What happens? If you remember, in the unique situation, we construct a stationary measure which I call rho. Right? Yeah. You will see from now on, I will call it mu epsilon. Why mu epsilon? Mu because I like to call the measure mu. And then this measure is indexed by epsilon. Why? What does it mean? It means the following. Epsilon is the size of the nodes. Right? So basically, when I put a node on the system, it depends on the strength of the nodes. For instance, here, I take omega in this set. Omega is a number between two small numbers, minus epsilon and epsilon. Why? Because the idea is what happens when epsilon goes to 0. So this is an important point in the Limit frame, which is called the stochastic stability. Basically, the idea is it true that when epsilon goes to 0, so when the noise goes to 0, this measure goes to mu, which is invariant, which is 30t. This is invariant. So let me give you a picture of what I'm saying now, because this is an important point. I didn't put on the slides because I wanted to explain in detail. Okay, so suppose you have a map T, right? Then we associate this, a deterministic map, with some measurement. Okay, so we have T, mu is a deterministic analysis. Then I take a neighborhood of T, and the neighborhood of T is measured by some epsilon. For instance, here epsilon, it is clear what it is, right? So basically here I take a map, for instance, T omega, where omega belongs to minus epsilon epsilon. So you see, if you take a map in this way, Tx plus omega, right? Omega is small. So basically, all this map T omega will be in this neighborhood, which is measured by epsilon. Okay? Everything is precise here. Okay? Now, if I choose the omega in an island way, so I'm looking to the unique situation, what I told you before, right? I have a stationary measure, mu epsilon. This is, from now on, I will call it the stationary mu epsilon. I told you why. Stationary. This is the measure which I use to do statistics and probability of my system. But this measure depends on epsilon. So what happens when the noise goes to 0? Is it true that mu epsilon goes to mu? Now, what does it mean goes? It could go in two ways, strongly and weakly. Weakly means you integrate this from step bounded function, continuous bounded function, and this goes to the integration of the bounded function with respect to mu. But there is also, okay, so weak means for any f continuous in no space, and also bounded because usually the space is compact, f d mu epsilon goes to f d mu. This is the weak convergence. And then you have the strong. The strong means we suppose that it will be the case that both are absolutely continuous with respect to the event. Right? So basically, mu epsilon will be a density times dx, and mu, there is a density h with respect to dx. And strong means h epsilon minus h in the 1 with 0. This is the strong, this is the weak. And this problem is called stochastic stability. Weak and strong stochastic stability. Why is it interesting? Because we don't have, I don't know, the last time we don't have the same kind of concept in the quotient setting. In the quotient setting, I mean, in the quotient setting which I'm looking, there is, we have this concept as well. I will tell you probably next week. We have also parameter epsilon, right? Which enters, which give you the strength of the nodes. But there is no explicitly said in this way the concept of stochastic stability. It's not clear in my mind. This concept here is very well posed in the lead situation. In the point check, we have to think about it. This is another stuff to look for. Right? Now, but why is important? Because this morning we saw some picture for the Lorentz system. Of course, the kind of perturbation method used for the flow doesn't belong to this set, of course, because here we have maps, right? But even in the case of maps, we can try to see if we can do something similar. For instance, suppose you have the known map. You know, the known map give you this kind of attractor. It's something, something to start, right? The known map is like, it's an attractor too. And suppose we have this attractor, is given by x prime equals some function of x, y, whatever it is, and y prime, another g, x, y. Okay. Something of this type. It's a math, not flows, not a vector field. We have an attractor. What happens if you put some noise, for instance, on one of the two variables? I have the noise, exactly like this one. And here, since we are in the plane, we don't have to put the mode 1 because here we have to put the mode 1 to prevent the map to go outside the interval if it is on the interval. Instead, a very nice trick to avoid the map goes outside with convolutions. Here I use the torus, so I don't care about it. But otherwise, you might be careful. But here, no, because we are in the plane. If you put epsilon, what happens? Okay, the attractor becomes fat. This is not the becomes fat. I don't know anymore if it is a fact of attractor. Really don't know. But the measure is not anymore. This attractor brings a singular measure, which is called the SRB measure, whatever. This measure here is not absolutely continuous, it's singular. And we know how it is done. It's a measure which is singular. I don't want to go into the details. It's a measure which is singular with respect to the data. But the stationary measure, which exists when you put some noise, which we call mu epsilon, is absolutely continuous. That kind of becomes fat if you look at it from the point of view of the measure. And then, when you set mu epsilon to 0, you have this convergence weakly. It's of course because these measures are not dense. Okay, this result is far from being trivial. Okay, it has proven by Viana and Benedus. I think on Angus or or some other conjugate. But why can you use this? Because when you are looking to systems which are perturbed, there are the way to measure how the system is perturbed are several ways. There is the structure stability, where you put some parameters, like we saw the example of microelectrics. But here we have a measured theoretical kind of stability, which is the stochastic stability. So the idea is to look how this measure, which is the stationary measure, which is in some sense the perturbed measure, which give us the statistics on the attractor, converge to the invariant measure mu. Okay. Of course, there are a lot of questions here, not trivial. For example, suppose we create stationary measure. When the epsilon goes to 0, are you sure we go this one or we can go once? or convex combination of angles. Okay. This is, okay, there is some theorems which tell you that sometimes this could be unique, but invariant measure for the original system not. You can go to convex combination of invariant measure which is okay, so there are, but it's not important. The basic idea is this kind of stability, which is stochastic stability, which is a stability in the probability sense, not in the topological sense, or in the differentiable sense. And this is typical of Garnici system, and next to it we see something not exactly the same, but something which could be stated more or less in the same way for the differential set. Okay. Okay, now let's go on. Okay, now from now on I will call the stationary measure mu epsilon for the reason I told you before, because the idea is, does this measure converge weakly or strongly to this measure mu when the noise goes to zero, for instance in this example. And this is the classical example of perturbation by additive noise. It's very important, even if it is simple, it's important to keep in mind this example. Okay, now let's go to example you see more deeply. Now I take some observable, okay, now I take my observable, G, we remember it was equal to minus G of x is minus log the distance is from the target point, this is the target point. Okay, yes. And now I construct a process, xz, which is given in this way. So basically, I fix z, and I look at the distance between z and the point of the trajectory. Okay? And then I consider the maximum of this sequence. So basically, okay, now let me give you a very precise geometrical meaning, because otherwise, if you see it for the first time, it's not clear at all what it is. And okay, so basically, sorry, maybe something. Okay, no, it's fine. I will tell you the geometric interpretation in a moment. Yes. Okay, so one now I forgot to write something, but I will write now. So I got it's probably written in the next one. Yes, okay. Okay, now take this sequence, it's written in the next one, but I can anticipate. So we have this sequence of random variables, right? X0 is 1. The Federal study a very simple problem which is given to students in any probability book. Namely, if you have this, look at this distribution. Let me call it U instead of T as in the probability book, because so basically this is what? See, this is the maximum, this is the probability that x0 is less than or equal to mu, x1 is less than or equal to mu, and xn minus 1 is less than or equal to u. Okay, this is the typical question. Right? Now, let me tell you, take this event here, xk less than or equal to u. What is this event here for the variable which I constructed? Okay, this event here is nothing but minus log of the distance of tkx z less or equal to u, right? Because this random variable xk is defined in this way, minus the log of the distance of the ether from this point. Okay? Now, to be say precise, this is all the quantities where we have this one, because this event will be measured by the environment measure, the stationary measure, whatever. But the randomness is here. The random variable is here. Right? And okay, so what is this section? Yeah? Okay, look, if you put -1 here and you Okay, so let's make it in detail. This is the distance t, k, x from z, right? Is larger or equal to e minus u, right? And so this is, so these are all the quantities for which we have this. So this is exactly the ball of center z and of radius e minus u, the complement of this ball. No, theta, sorry. Is this one is, just a second. Yes, the ball. No. Wait a second. TK. No, for the moment, let's write it in this way. Yes, it means, okay, it means that TK, it means what? TKX doesn't belong to the board of center, not precise, of center Z and of radius E minus U. Okay? Because the distance between this point and Z is zero. So it means this point here doesn't belong to this center here. So it means what? If you look at, this makes the connection between recurrence and this theory. It means the following. I have here my ball of center Z and radius E minus U. Okay? So the index x0 less or equal to u, x n minus 1 less or equal to u, is exactly equal to all the point x for which x doesn't belong to this ball, and also tk minus 1 x doesn't belong to this ball. Okay, so this is the geometric interpretation of the distribution. So the distribution of this, and okay, if I take the probability p, in my case, this will be the stationary dimension, the time of time theta to the power n t, because I want to put some stationarity here, because otherwise I'm not able to do the computation. But what is important is to understand the geometrical meaning of this event. Okay? So this event here are all the points which start somewhere, and for the first n minus 1 iterates are outside this ball. Okay? So this is the connection that people found between the distribution. This is just the distribution function of this random variable, which is equivalent to this one, right? And the particular probability which we take in the random, I need the setting is exactly this one. Why? Because we want to do a stationary theory. Okay, so this is important. Why? Because if you want to do the stationary theory of random, of extreme value theory, we have theorem which help us. But if you want to do a extreme value theory for non-stationary process, what I will tell you next week, you do something else. And identity entity. Okay, so the message is, if you have a stationary process, and in our case, this process is stationary, if we use this method, we know how to do it. Okay, it's not easy, but we know how to do it. But if the process is not stationary, for example, sequential, non-autonomous, you must be careful. So our result, I will tell you next week how can we handle this. But this is an important difference. Anyway, okay, so I take this, and so now with this measure here, which is for which the process is stationary, I want to study this distribution. That's it. Now, how can we do it? Okay, now I will tell you something. This something which becomes clear later on, but for the moment, I have to, you have to believe me. Okay. I will tell you why in the next steps. Consider now the distribution of the first variable. So in some sense, all the variables are the same distribution because that's a stationary process. Okay? So take the first one and look simply to the distribution function of the first, which is the same for all, because the process is special, right? So this is exactly, since n is equal to 0, this is equal to this guy here. Okay? In our case, for the observable, this is just the stationary measure of what? Of the points which are outside the ball. Okay, so let's continue. Okay, now suppose that there exists, for any positive number, we can find a sequence of numbers for which n times 1 minus the distribution function of, the distribution function of, distribution function of one of the variables, because all have the same distribution. Suppose that we can verify, suppose we can verify this. Let me try geometrically this, because this is interesting. What is this condition for our observable? It's something very easy, which is this. Look, since I take 1 minus, this condition here, n times 1 minus f un, going to tau, where tau is any chosen number, is exactly this n times the measure, the units of the ball of center z and radius e minus un. This must go to tau. So it's a very easy way to write this condition. This is a condition which must be verified. Okay? For any tau, positive tau, we have to find a particular sequence which verifies this thing. Now, look, if for some reason this measure is not atomic, this can always be verified with equality here. So for any fixed tau, I can always find a un, which depends on tau, of course, which verify this one. Why? Because if you have a measure which is not atomic, then if you have a measure mu of a ball of center potential and radius r, and the measure is not atomic, this function is continuous in L. It's continuous in the radius. And so if you fix here tau, we can always find mu n and verify this. If not, you have to prove there is some sequence for which the unit is obtained, is attained. Okay? But think to it in terms of a non-atomic measure, which is easier. And so the question is, we say that we have extreme value theory if we have this. So basically, but look here, that in contrary to what we do in probability, we cannot take u as we want. We have to take u which depends on n. And the dependence is given by this one, by this one. Someone could ask why this complicated stuff. And the reason is very simple. This is an exercise which we did in certain probability. For instance, suppose the variable and n are IID. In our case, they are not. Because since this variable are moved by, the system random or not, they are not, I mean, the distribution are medium this one. Okay, so the distribution is the same, but they're not independent. Okay, so I told you before that the distribution of the variable is the same, because the measure is stationary, but they are not independent. Okay. Suppose they are independent. Okay, so the computation is trivial. Okay, so what is the probability mn is less or equal to un? Okay, so the mn is written in this way. The probability of a sequence is the product of the probability of the single variables. And I have this one. The probability of each of them is 1 minus the probability is larger than n. Okay? And then, if I choose un in this way, exactly in this way, the computation is given here, and they get something which is reasonable, E minus tau. But if this UN is independent of n, we get a degenerate distribution. So this guy could go to 0 or 1, which is not interesting. I mean, it's not mysterious. It's exactly what happens in the central limit theory. In the central limit theory, if you want the central limit theory, we have to construct the process exactly as we did. We take x, we take the sum of xn minus n times the expectation, and we divide it by sigma square root by the square root of the variance. If we do not do it, we don't get anything. Here is the same. If this has some meaning, at the end, we have to take this number, not as we want, but we have to relate this number to n. For me, how we do it in this way? So we ask that the distribution functions, one of the values are the same, verify this equality, asymptotically, or for any n, if the measure is not atomic. And if we do so, we ought to get, okay, if doing so we get this, we say that we have an extreme value law. Okay, look, this must be proved when the variables are not independent. If the variables are independent, the proof is treated. It's exactly the okay. So you see, the next step, when people, okay, what people do in dynamical system, apply to probability, want to try to apply to dynamical system the idea of probability. So when they saw this result, they said, okay, this result is true if the variables are independent. What happens if the variables are not independent? But we know in dynamical system, the independence could be replaced by strong decay of correlations. So the correlation became sufficiently fast. So the process became independent as entropy. It is exactly what motivated a lot of people to look at this situation in dynamical system, when, for instance, we have the observer are dealing this way. Okay, so we take into account the dynamics. So repeat, this value at the same distribution because the process is stationary, which is fed to this measure, but there are still independent, and we have to prove it. And this is exactly what people begin to do. Okay? Okay, more generally, here I am repeating what is going on. Now I go a little bit faster. In general, what people want is the following. The formulation of extreme value theory in huge generality is the following. We want to study this. We want to study this. This event here. Actually, I forgot to put the probability, whatever it is. In our case, is the product measure. We put some probability here. We want to see if this goes to some function of theta, where tau must verify this one. Okay. So this is an assumption. If with this assumption we can prove it, then we say that we have an extreme value theory. This is the way, the abstract way to do the theory, right? Now, in the previous example, I showed you that the asymptotic, what we got asymptotically was E minus tau. There was a particular case which was constructed having in mind the IID case. But in general, it's not what people obtain. What people obtain with this kind of observable is something different, is E minus theta tau, where theta now is a number between 0 and 1. This number theta, for people working in application of extreme value theory, in particular in climate, has an important meaning, is what people call extreme magnitudes. Why? Because this number is important for application. Let me anticipate why, then I will tell you later on. Okay, so look at the geometric interpretation of what we did, right? So basically what we did is, we take a point x and we look where it is far from this ball. Okay? Now, if suppose the point z is any point in our space, okay? So we know that by Poincaré theorem, which Michael reminded several times, that the probability to enter this ball when the radius became small is very small, periodicity in particular. Because, okay, the probability to enter this became almost zero, became zero if the ball becomes very small. But suppose this point Z is a periodic point. If you have a periodic point and you take a point which is close to it, of course this point go away, right? Because by quantity theory, each point must go everywhere else. But if the point is periodic, by some sort of continuity, the speed with whom this point go away is less than if point is not periodic. In some sense, if the point is fixed or periodic, a point which is close to it takes more time to escape from it than if the point is not periodic, intuitively, and by continuity is true. So this number here, theta, measures this effect. So if the real set, so the point Z is not periodic or fixed, this point theta is exactly equal to 1. But if the real set, or if you want the set which are looking for some reason, in a climate reason, is around a point which is fixed or periodic or invariant, this point is less than 1. So if this less than 1, people say we have clusterization of the orbit. So the orbit here takes more time to escape than if the point is not periodic. So for this reason, this number is called, or the reciprocal depends from the authors, is called the persistence index, and is used, I will tell you how later, just as a new indicator to describe some phenomenological event in climate theory. I will have a picture for you. So this is why I collaborated with this guy, because
so in practice, what happens is that if the real event is near to something periodic, in practice you can have a cluster.
Yeah, exactly.
When you randomly fall near to the real event, you will have a cluster of.
Good question. What happened in the random setting? Okay, I tell you.
Okay.
In the random setting, no, because it's completely right. In the random setting, the notion of periodicity disappears. In fact, what happens in the following is true that it disappears, but what can you, okay, but it depends on the distribution of the noise. I'll give you an example. So, for instance, if the noise, in the new situation, what you did for it, if the noise is absolutely continuous, so if the measure which I call theta or m at the beginning is absolutely continuous, if, okay, the extremity is equal to 1. In all the example which you will check, okay,
So the noise can kill this problem
completely. But if the distribution of the noise is discrete, for some reason, I will example, the extremity is better than 1.
You can recover the same situation.
Exactly, you understood that. So we don't have a parent periodic point, feature point, but you can have, we can reconstruct some kind of periodicity using discrete noise. Even in the quench situation, this happens. For instance, one of these guys, Pascal Yu, which worked on climate, he asked me the following. Instead of looking to a target set, which is around the point Z, and to establish this theory, what happens if the target set moves randomly? So I look to a point there, which is, suppose the point is typical of some time starting or panorama, whatever. The point or the radius of the set moves randomly. So what we did, we took the radius, which is not random, but the point is random. So the rare set moves randomly in their need way. So we took some distribution which verified their need properly. Can we get an external index which is not 1? So can we reconstruct some kind of clusterization, even if there are no periodic points? And the answer is yes. It's very easy to construct examples, but the examples are extremely easy. I mean, you take 4 or 5 maps, you look some configuration of the maps, adopt, construct, but it's enough. It's an example, right? And we take 4 maps and 4 rows, and the center of the road moves according to move between 4 positions, and we have 4 maps, and in this case we can compute this number precisely. I will tell you how, and this number is less than 1. So moving, we call it moving target. In the moving target, you can have clusterization even if you put some noise. But the noise has a discrete distribution, not a continuous one. Okay, no, this is just very, again, it will be good with transparency. These are very general considerations, right? Okay, so, but this consideration play a role now for application, so I have to tell you, because I promise you to tell how we can use it in practice. Okay, so if you go to the book by Lindbergh, Leadbetter, and the other guy, you will see that the theory is presented somehow in a different manner, of course equivalent. So therefore, the sequence UN, which I put here, we put in N, because as I show you, if we don't put N, we get a trivial distribution. Therefore, UN in this way. Y plus IN plus B. This is historically the beginning in this way. And where IN is positive, in the end is not less important. Then they prove the following theorem. This proof is not easy. What is beautiful is okay, the central limit theorem is not easy. I mean, the proof when the variables are binomial, I think it's given a lot of years ago. Now we can do it by hand without using sophisticated technique, but it's not completely trivial. But it is only for the binomial. If you want to put the CFT for any random variable, even IID, if we don't have the characteristic function, I don't know how to do it. So you need all the V theory of characteristic function and so on and so forth. But to prove the theory, which I'm going to tell you briefly, really the proofs are simple, but ingenious. So they were given by Frechet, Kittek. It's really basic analysis, but the construction are not bad. And they prove the following deep result, according to me, is of the same level of the CFT. They prove the following result. In the I indicator, and then using mixing, we can generalize it. But the proof in the non-I indicator just mimics. So when the variable IAD, okay, this distribution here converts if it converts, and then there are conditions to do it, but if it converts, this asymptotic function could be known of 2 types. But so gamma and Frechet value. Okay? So these are cumulative distribution functions, not density. So basically, if you look at the picture, there are, that's each type. So this is one, they go this way, right? They are cumulative distribution functions, not density. But there are only 3 types. Okay. When the variables are not independent, we can recover the same, provided we replace the dependence with condition, which I recall in a moment. But I will not use it for this view. I will do something different, which are called D1 and D2. This is the terminology used by Leadbetter, which in some sense allow to replace independence with mixing. Okay? But the message is, if we take this normalization for UN written in this way, then we have, and we introduce this parameter. This is, if this exists, this limit exists, in the continuity point of this function, as usual, right? So this function can be all of 3 times. and this function are done in this way. So this is the discovery. For instance, in our case, if we take our measure, mu epsilon, is exactly the bed, then what we get is this limit here. And we use this sequence UN just written as I did before, using this way. If you take the exponential, whatever, and you rewrite E minus UN exactly in this way, so introducing this parameter Y, which it became in our case E minus 6, and this is the number. It's one of the three. And this is just obtained using our observer. Why? Because for our observer, we know that this limit can exist. This case is given by this law, which is one of the three. Okay. Now, why I told you this? Because we came to the second application of this. Told you about the Striemann index, but I never went into the detail. Here we can go. Okay, now, since we have three possible distribution, cumulative distribution functions of this type, how to discriminate between these three? And people invented what is called the generalized extreme value J distribution, which is a distribution which depends on three parameters. And there is a link between the parameters of the distribution and the number an and bn which we found before. An and bn. Okay? So basically, if you can say something about these numbers, C, sigma, and kappa, these numbers are related to the number an and bn. Why this is used? Because suppose for some reason, and this is the theory which they use, supposing for some process, for instance for the process which we study, right? We know that the law which we obtain at the end is, for example, the Gamble law. But this must be or proved or assumed. This is the role of the mathematician. So you give me a system, I tell you, okay, I can prove that this is the distribution, or if not, we can assume reasonably that this is the distribution. Okay, so let's go now to this. Now the idea is, if I know that the distribution at the end is of Gamble type, so it's like this, right? So what I can try to do is to tune these three parameters, namely sigma, kappa, and psi, in order to get at the end what we expect to have, in particular the Gamble law. Okay, but why is it important this one? Let me tell you why. Because these three numbers, or two in this case, because one goes to 0, so basically sigma and kappa are related to an and bn. Okay, so what? Okay, look. Now, take this condition here. Remember this condition? This condition for R fits the way. It fits the way, right? This condition can be written in this way. So this event is exactly this ball, right? If I fix time, I can write it explicitly. This ball here, I put n. I don't remember why I put n, it doesn't matter, forget it. This measure here is written in this way. Okay, so, yes. Each measure, okay. If you do some measure theory, you know that one quantity which is important to study is the following. You take the measure of a ball of center Z and radius R, you take the logarithm of this guy divided by the logarithm of R, and you ask yourself if this limit exists. Okay, if this limit exists, this gives what people call the local dimension of the measure mu in the point Z. This is a kind of fraction. If the measure is the vector absolutely continuous, this number in dimension 1 is basically 1 everywhere. But otherwise, this number depends on the point Z, and it's an estimate, a local estimate of halves of the dimension of the invariant set. There are a lot of, if the limit exists, otherwise you take the soup, the limit exists, right? Okay, and in some cases it exists. The numerical system, one can prove that almost surely it exists. Okay, so if this limit exists, you see that the measure of this ball can be written in this way. So you see, UN is here, multiplied by some experiment, which is exactly this guy. But since we have a relation between the parameter of the generalized extreme value law, sigma and kappa, and this n in the end, here you see sigma minus 1 is Bz, exactly this dimension. And kappa is also related to this dimension. So this has a spectacular application in time. Why? Because people said, okay, I suppose my process goes to some Gamma law, which is what happens in the system is enough chaotic. Because if the system is enough chaotic, inside of independence, we have strong determinant correlation. So in this case, we assume reasonably that we have a Gamma law. But if you have Gamma law, what happens? Then I can compute this number, kappa and sigma, associated to UN. Because this is related to AN, this is related to BN, but the AN and BN just enter UN. Okay? And so, if you compare everything, you see that sigma minus 1 is Bz. So it's exactly the local dimension of the point Z. So what people did is, they have free space, imaginary space, they take point Z, and they look at the convergence to the Gamma law around this point, using this observable here, exactly this one. This one. Well, this one. Okay? This one. Okay? And so they were able to compute just using the convergence to the Gamma law and the relation between this sigma and the exponent of the measure, so basically the local dimension, they were able to characterize the local dimension of points in the phase space. What does it mean? Okay, according to them, if this local dimension changes, it gives you some information on the situation of the dynamics in this particular part of the phase space. Okay, and now, okay, I skip this one because this is last matter of the next week. But I want to give you now. I want to give you the application, immediate application of this what I'm telling you now. Okay. So here, these people took the Lorentz attractor, which Michael detailed during his lectures, and this is just, it's not, I mean, it's not a test on real data, it is just on the Lorentz. Then I will give another slide with real data. And what they did is, using this approach, they really compute the local dimensions. So basically, they take a rare set, namely the point Z, in different regions of the phase space. They assume, because it's reasonable for this kind of system, that we have a Gamma law, because the mixing is enough strong, and so they tuned the parameter of the generalized distribution function in such a way to get the limit law, which is known. But in doing so, as a counterpart, they were able to compute this number. And this number changed according to the position. It is beautiful. So basically, and they were, okay, so if the number is small, it means in some sense there are less concentration of points in some region. So they were able to measure the concentration of points in the phase space according to the value of mu. And they get this picture. And then I finish, no, because it's time. there is another picture which I will explain more next time, which is this one. This is taken by real observation now, where they constructed a graph where they put on one axis the local dimension, so in any point they compute the local dimension according to this formula, and then on the other axis they put what they call theta, the external limit. Even if I didn't tell you how to compute theta, we will give you the formula next week. This can be computed, and you see, according to with me, and then you can compute this graph. And in each point you have two coordinates, the dimension and theta. And then they interpret, but I will give you the interpretation I will show you next week. They interpret this phenomenological graph according to your real observation. You see, these are patterns which can be described physically and phenomenologically in a very precise way. And each of these patterns coincide with some points in this space. And this paper was published on Nature. So I mean, they were lucky. good stuff. And okay, so next week what I'm going to tell you is more information about theta and how can we obtain this kind of distribution using a spectral technique. This spectral theorem was proved a few years ago by Gerhard Keller and Lorenzo Liverani, and then Gerhard Keller showed how to apply it to study the distribution of events like this, and then we applied it to random situations. Then this situation is not too difficult, then the quantity situation is a bit more tricky. But what is interesting in this technique is it avoids a lot of assumptions people used before. But this technique, which is very powerful, and this technique will give you exactly this number, exactly, as a disadvantage. It works when the system has what we call spectral gap. So when more or less the correlation behaves exponentially fast. Otherwise, it doesn't work. You have to replace it by other techniques. But I will tell you more next week, which will be a little bit more technical because I will introduce this object here and we'll see how to work with it. Okay, stop now because it's 2 hours of time.
Questions?
Yes.
Maybe I just missed the reason. The first is I don't know if this is what goes wrong in terms of the system.
No, the endomorphism on the driving.
Sorry?
On the driving space.
Yes. Well, you said you need is important to have the sigma which is
Invertible.
invertible. And it is not invertible, you have anything in this.
But if it's not invertible, the point is if it's not invertible, I cannot get the equivalent measure. So I do not.
Is it something that you can never get or?
No, it's even more easy.
How?
The result different is really even more easy. So what you can get is just a measure which is independent of omega, but as not in Arnold, sorry. Arnold wrote explicitly this is very rare. Yes, because in a lot of example, interesting is very rare that all the map preserve all the map omega preserve the same measure. Almost impossible.
Any question, but I will ask you.
Yeah. Well, I think I will show first of all how we attack the Arndt case for this value using the perturbation theorem, and then I will tell you how we get the same using the branch situation, using the same spectral technique, by the way.